He is a fourth-year PhD student at Rochester Institute of Technology. He's currently a visiting research assistant at the USC Information Science Institute under Andrew Schmidt.
German, come on now.
Yeah, okay. Yeah. It's unusual to say it in German. Okay. The work in this presentation was during Sam's internship at the USC.
Okay, thank you for that introduction. Today I'm going to talk about my work, high-level hardware software embedded system design with Redsharc. This is a collaborative effort between me, myself, and Matt French at USC ISI. Just a quick outline. We're going to start with the motivation, give you a little introduction to Redsharc. What is it? What have we been doing with it before? We'll go into a little more detail. We'll look at a couple applications and show you where we tend to go with this. So to motivate this talk, the complexity of multi-processor systems on chips is ever increasing. We started with just having one core, one hard core, now we have a soft core, now we have hardware accelerator cores, then you have on-chip memory, off-chip memory, and you have to connect all of these things together and get them running successfully. So you need to control it. So how can we design these systems? Well, normally, you can approach this systematically. You start by constructing your algorithm, figuring what types of kernels are going to be in it, how they should connect together, what are the data dependencies. Then you implement each kernel, whether it's in hardware or software, choose a configuration of the system, so many hard cores, soft cores, accelerators, etc. Determine some networking approach. And then, of course, take your design, your application, and schedule the work onto those cores. So our approach for this is the reconfigurable data stream hardware software architecture, which we call Redsharc. It was originally inspired by the streaming virtual machine from the DARPA Polymorphic Computer Architecture program. It provides rapid construction of SoC systems, allowing you to explore this design space by getting the system designed quickly and testing different variations. Redsharc is a system infrastructure of networks and interfaces that allow you to connect your cores together using predefined and verified networks. But most importantly, I want to differentiate this from what's been said so far. Redsharc is not a high-level synthesis tool. Redsharc is a tool for connecting cores together on a network. So Redsharc supports the use of generating hardware designs using HLS tools. So if you're designing software, you use a compiler. If you want to design hardware, you can write it by hand, or you can use an HLS tool to generate it. And then we integrate that into the network. So Redsharc is two parts. First of all, it's an API that allows standard interfaces for software and hardware kernels that directly connect those kernels to the networks on chip. It's also the architecture. Those networks, streaming or block-based. There's libraries for software to utilize that, as well as hardware interfaces that wrap around your logic. So Redsharc has been around before, so what did we do this time? So we simplified the design entry by specifying specific developer roles, allowing different types of people to come in with their unique expertise and apply it in such a way that they can work together. We incorporated software to hardware kernel flows. Let's see, what else did we do? Automated control kernel generation. So when you want to take your application and run it and schedule all those kernels, you need a way to manage that scheduling. So what does a Redsharc system look like? Well, you have your cores, hardware and software. You have then the kernels that are running in those cores. If you have a hardware core, you can implement two kernels next to each other and directly connect them. If you're implementing in a software core, you can context switch software kernels on and off. Then you have the networks that connect the cores together, a stream switch network and a block switch network, and the memory that's connected, and then finally that controller. So stream switch network provides a point-to-point interface between cores. So what this is a FIFO, so we can connect one core directly to another one. The block switch network provides random access memory to a core. So if a particular core needed some scratch pad space that then was going to turn into the output result of that kernel, then we could take that memory location and provide access to another kernel at a later time. So Redsharc is a front end, and it's a build framework. So you can input your application by specifying the kernel implementations, by specifying the data flow graph, there's data dependencies between the kernels. You can specify the configuration of the system, and then the scheduling algorithm that you want to apply to it. Redsharc then takes these, compiles the binaries for the processor cores, it synthesizes the hardware cores, it also synthesizes that network connection between all of those cores, and provides the bit streams that then you can come out, download them to the board. The controller is already synthesized, so you can then just run your application. So the controller here is an introspective controller. It has three main functions: to schedule, to monitor execution, and then to perform that actual control, specifying the switches. So Redsharc defines three developer roles. An applications developer is a domain expert that solves a problem by constructing algorithms by incorporating various kernels. A kernel developer is this applications expert that's coming in and writing the software code, designing the hardware kernels, and then finally a systems developer that can come in and decide what the scheduling algorithm should be, how things should be networked together. So for each of these, we've defined an API or interfaces for those developers to use. And we'll go through each of these in the next slides. So we'll start with the kernel developer hardware software interface. This is something that's been done before, but I'll touch on it just to give you the background moving forward. If you're a hardware kernel developer, you start with your user logic, you connect your memory that you're going to operate on, then you can abstract where the actual location of the memory is. So you can use the same VRAM interface for your logic, but then at the back end it's connecting to this block and stream interface. Then this gets wrapped up with our hardware kernel interface, and then this core can connect to our stream and block switch networks. On the other hand, if you generate a core with HLS, that core, using directives, can already come out with specified VRAM or FIFO interfaces. So then we just take our hardware kernel interface wrapper, wrap it around that generated core, and we can connect it just like user-generated designs. Similar for software, we have a library of functions that interface with streams and blocks. The software stack looks like this. You have the user software that uses the software kernel interface that then runs on some microkernel or RTOS. This RTOS just allows us to come in and manage the execution, telling a processor core when to launch a kernel, the duty cycle between two simultaneously running kernels, etc. So at the end of the day, the data accesses are abstracted from the kernel implementation. So thus far, we've talked about the software and hardware kernel interface. Now we'll look at the data flow graph, system, and scheduling APIs, and then how these are all wrapped up together to generate this control kernel. So the DFG API, this is where the applications developer is going to come in. They're going to know what the kernels are and how they should be connected together. So you specify the number of kernels in your application. In this simple one, we have 2. And you can specify that each kernel and give an indicator to what functionality should be executed when that kernel is run. You specify the number of inputs and outputs. You can specify initial data, and then the output from each kernel, whether it should be a block or a stream, how much space you need. And then these can be used during scheduling to determine how much memory to allocate. Should it be block RAM? Should it be DDR memory? But most importantly, you can also specify the dependencies between the kernels. So here's 2 block dependencies, but also we have output stream and stream dependencies as well. Once you've specified your data flow graph here, there are 2 scheduling interface functions that are built into Redsharc. These are already defined and developed by us. They allow the scheduling to check and see if there are any unassigned kernels that should be then assigned and executed. And then if there are any kernels that are still running, so they can wait and manage it as the application finishes. For the system, we can specify the number of cores that will be in the system, and then for each core, specify the type, and then the number of kernels that can be simultaneously executed on that processor core. And then for the system, there's a scheduling interface function to determine if there are any idle processors. And this allows the control kernel to check and see if it can perform scheduling inside the kernel. Lastly, the scheduling API is a set of 2 functions. They're implemented by the user, and then these functions are used to perform the application runtime. So can schedule just checks to see if an algorithm is ready. Assign kernel does the same thing, but actually makes the assignment to that kernel and then launches it and begins execution of that kernel. So these two functions are implemented by the user. Okay, so here's how we wrap it all up. The control kernel uses this simple mechanism that's provided by us as default, but it's something that could be configured by the user if they need a different approach. Control kernel comes in, checks if there's any unassigned kernels, and then if there's processors that are available, it can schedule them and then actually launch that kernel. And then the control kernel lives until all the kernels have completed. So just to show you how it all connects together, here's the DFG API, here's the system, and here's the scheduling. Okay, so Redsharc has been around before, so there's a previous works that I have overwritten the reference here at the bottom, but I'll provide it if needed, to look at how the infrastructure performs. And so they've analyzed the block switch network. We can get really high data rates on chip. The stream switch network also performs very well. And then the hardware kernel interface resource usage is very small. So it's as thin as can be. So two applications. The first one is BLAST, basic local alignment search tool for bioinformatics. In this work, the goal was to see what the overhead was of the Redsharc network. If we could come in, how much could we scale the number of cores and how would that affect performance? And we came out with the results that there's a little bit, but we can scale near linearly. The second application, this face recognition, the goal is to take initial software version and slowly begin merging it into an SoC system. So we have this application, we initially implement all of the kernels in software, then we can take each one, so initially they're all implemented in software. We have a version of Redsharc that runs using pthreads on a regular PC. The same implementation using the API is then used in a Zynq SoC, so there's no change required by the developer to move from pthreads to some embedded processor. At this point, we have it running all in software on a Zynq ARM core. We've also been able to use HLS to produce the hardware kernels directly from the same software source. So moving forward, we'll implement more kernels. We'll also implement all of these kernels statically during the system generation, but the end goal is to use PR to configure these kernels at runtime and allow that scheduling to determine what should be programmed when. So to conclude, Redsharc is a set of simple user APIs, software and hardware kernel interfaces, data flow graph, system configuration, and scheduling. We improved on the Redsharc infrastructure that existed before. We simplified design entry, standardized representation of the application. So now, at this point, that intermediary layer is standardized, we can then begin building back and adding more front-end tools to allow the developer to start with some high-level version of their application and then more automate that process. The runtime control for the system has been automated, and now that the hardware and software kernels are abstracted from the actual storage location, we can do runtime configurable data locality as needed for performance. We're also implementing this as vendor agnostic as possible. So right now we have it working on the Zynq. We're also have an implementation on the Cyclone 5 SoC. And these are the cores that we're targeting at this time. Okay, that's it. Thank you.
So we have time for questions. No questions.
Okay, so do you support pipelining among the hardware module and the software functions?
Yes, so in a hardware core, you can implement multiple hardware kernels next to each other, so they would be directly connected in a pipeline fashion.
What, among the software and the hardware part? I mean,
Yeah, with streaming, sure. You could directly put them together in a pipeline fashion by streaming data from one core to the next core.
Have you looked at the IP Exact framework, which has sort of Eclipse plugins and synthesizers connecting up system-on-chip components in a similar sort of way?
We're aware of it. I don't know, was there more of a question?
Well, the question is, you're emphasising a particular application which is flowing between these components. So what does your infrastructure have beyond what you would have just for assembling the IP blocks on a chip, where some of them happen to be synthesized at the point of assembly, which is what IP exact does?
So if you did it that way, then your entire system is fixed. It doesn't allow you to do partial reconfiguration. It doesn't allow you to abstract what your kernel's doing from the capabilities that you determine for each core. So you can have multiple cores with more or less resources and then put kernels on them as needed during runtime. Maybe you have two versions of a kernel, one that uses more resources, one that uses less, and then at runtime you can determine which one to use.
Questions? So the thanks again.